In 1995, astronomers found a planet orbiting 51 Pegasi, a sun-like star 50 light-years away. The planet was a gas giant half the mass of Jupiter, but it completed one orbit every 4 days. Jupiter takes nearly 12 years. The discovery violated every formation model astronomers had built from our own solar system, where gas giants orbit far from their stars in slow, wide circles. 51 Pegasi b became the first confirmed hot Jupiter, a class of world that orbital mechanics said should not exist. Since then, surveys have catalogued hundreds more. Some orbit even closer. WASP 12b circles its star in 26 hours. WASP 19b finishes an orbit in 19, and WASP 103b, located 1,400 light-years away in the constellation Hercules, completes one revolution in just 18 hours and 50 minutes. At that distance, the planet's atmosphere reaches 1,600 degrees Celsius on the day side. Tidal forces stretch the planet into an egg shape, and orbital decay measurements suggest the planet is spiraling inward, losing altitude with every pass. Hot Jupiters challenge the standard model of planetary formation because gas giants require vast amounts of hydrogen and helium. Close to a young star, radiation and stellar wind blow light elements away before a planetary core can accumulate enough mass to hold them. In our solar system, Jupiter and Saturn formed beyond the frost line, the distance where water ice and other volatiles could condense. That boundary sits around 5 astronomical units from the Sun. Jupiter orbits at 5.2. Hot Jupiters orbit at a few hundredths of an astronomical unit, well inside the orbit of Mercury. The contrast is extreme. Where Jupiter receives sunlight diminished by distance and cold enough to freeze ammonia, hot Jupiters endure temperatures that vaporize iron and create winds faster than the speed of sound. The leading explanation is planetary migration. According to this model, hot Jupiters form farther out, where conditions allow gas accumulation, then move inward through gravitational interactions with the protoplanetary disk or with other planets. Migration can happen smoothly over millions of years as the planet exchanges angular momentum with the disk, or violently in a few thousand years if a close encounter with another giant planet flings one inward on a highly eccentric orbit that tidal forces later circularize. Both paths end with a gas giant parked closer to its star than any planet in our system. The process erases the initial conditions, leaving only the final configuration and a few clues in the orbital architecture of any surviving companions. Astronomers confirmed the existence of hot Jupiters using the radial velocity method. When a planet orbits a star, the star also orbits the shared center of mass. That motion produces a periodic Doppler shift in the star's spectrum. The technique works best for massive planets in tight orbits because they produce the largest velocity changes in the shortest time. Michel Mayor and Didier Queloz used a spectrograph at the Haute-Provence Observatory to measure the radial velocity of 51 Pegasi and detected a 50-meter-per-second oscillation with a 4-day period. The measurement implied a companion at least half Jupiter's mass, orbiting at 7 million kilometers, 1/8 Mercury's distance from the Sun. The discovery paper was published in Nature in November 1995. Independent confirmation came within days. The finding was so unexpected that some astronomers initially questioned whether the signal might come from stellar pulsations or star spots rather than a planet. Subsequent observations ruled out those alternatives and established the planetary interpretation as the consensus. Transit photometry later revealed the physical size of these planets. When a planet passes in front of its star, as seen from Earth, the star dims by an amount proportional to the planet's cross-sectional area. Ground-based surveys like WASP the wide-angle search for planets, and space telescopes like Kepler recorded thousands of transit events. WASP 103b was discovered in 2014 using 12-inch robotic telescopes in South Africa and the Canary Islands. Follow-up spectroscopy measured the host star's motion and confirmed the planet's mass at 1.5 times Jupiter's. The transit depth showed a radius 1.6 times larger than Jupiter, meaning the planet is less dense, its atmosphere puffed up by the star's heat. That inflation is caused by intense stellar radiation depositing energy deep in the atmosphere faster than the planet can radiate it away, creating a bloated envelope held loosely by gravity. Hot Jupiters are not stable over billion-year timescales. Tidal friction converts orbital energy into heat, causing the orbit to decay. The same gravitational forces that stretch the planet into an oblate shape also dissipate energy as the interior flexes with each orbit. For WASP 12b, astronomers combined transit times from 2009 through 2019 and detected a shift consistent with the orbit shrinking by 29 milliseconds per year. At that rate, the planet will collide with its star in roughly 3 million years. WASP 103b shows similar signs. Repeated observations between 2014 and 2021 recorded transit timing variations that match an inward spiral, though the uncertainty is larger because the baseline is shorter. The decay rate depends on the internal structure of both the planet and the star, quantities that remain difficult to measure directly. The James Webb Space Telescope observed WASP 103b in 2023 using its near-infrared spectrograph. The data revealed water vapor and evidence of high-altitude clouds made of silicate particles. The temperature profile showed a thermal inversion, where the upper atmosphere is hotter than the layers below, likely caused by absorption of starlight by titanium oxide or vanadium oxide. These observations do not change the migration conclusion, but refine the atmospheric models and help distinguish between different heating mechanisms. Even in these extreme environments, molecular chemistry survives, and weather systems driven by temperature contrasts between the permanent day and night sides redistribute heat across the globe. The detection of hot Jupiters forced planetary scientists to add migration to their models. In the classical picture, planets form where we find them. Gas giants stay beyond the frost line. Rocky planets stay inside. Hot Jupiters proved that picture incomplete. Planets can move. They can scatter each other. They can interact with the disk and drift inward or outward over millions of years. Migration is now understood to be common, not exceptional. Jupiter itself may have migrated inward early in the solar system's history before reversing direction. A scenario called the Grand Tack that would explain the asteroid belt's truncated mass and Mars's small size. That reversal may have been driven by Saturn's formation, which changed the gravitational landscape and halted Jupiter's inward drift before it could sweep the inner system clean. One question remains open. Why do we find hot Jupiters at all? If tidal decay is inevitable, why haven't they all fallen into their stars already? The answer may be observational bias. We see hot Jupiters because they are easy to detect, and because planetary systems are still young. Most stars in hot Jupiter surveys are a few billion years old, and their planets have not had time to complete the final inward spiral. Alternatively, some process may slow or halt migration before the planet is consumed. Magnetic interactions between the star and planet, or resonances with other planets in the system, could act as brakes. Some systems may also host multiple planets that stabilize each other's orbits through gravitational tugs that counteract tidal drag. The data are not yet decisive. Future observations will test these scenarios. The extremely large telescope, under construction in Chile, will directly image the atmospheres of hot Jupiters and measure their composition in detail. Long-term monitoring campaigns will extend the baseline of transit timing measurements, reducing uncertainty in the decay rate. And surveys of older stars will reveal whether hot Jupiters become rarer as systems age, which would confirm that tidal in-spiral dominates, and that what we see today is a snapshot of worlds in their final million years. If hot Jupiters are absent around stars older than 10 billion years, that absence would set an upper limit on their survival time and constrain the strength of any stabilizing mechanisms. It would also clarify whether what we are observing is a transitional phase or a persistent feature of planetary architectures across the galaxy. The existence of hot Jupiters also raises questions about our own solar system. If migration is common, why does our system lack one? The answer may lie in timing. If Jupiter's inward movement stopped early enough, before the terrestrial planets finished forming, the inner system could evolve into the configuration we see today. Systems where migration continued longer may have lost their inner rocky worlds, with the gas giant consuming or ejecting them before settling into a close orbit. That process would leave single hot Jupiters with no companions, a configuration observed in many systems. Other surveys, however, have found hot Jupiters with distant outer planets, suggesting that not all migration is catastrophic, and that some architectures can survive the upheaval intact. WASP 103b orbits too close. Every 18 hours and 50 minutes, it completes another lap, losing a little more altitude, absorbing a little more radiation. The discovery of this planet and others like it showed that our solar system's orderly arrangement is not universal. Planets migrate. Gas giants can end up where formation theory says they never belonged. And some, orbiting in hours rather than years, are already falling toward the stars that made them impossible. The measurement of their decay, the mapping of their atmospheres, and the search for stabilizing forces will tell us whether these worlds represent a brief phase in planetary evolution or whether some mechanism we have not yet identified allows them to persist far longer than current models predict.